Okay, so in the previous video we talked more about inverses and how we represent inverses using that -1 as an exponent. Today we're going to look at, in this video, how to determine if two functions are inverses of each other. Now this is very important. This is what we call the inverse function theorem, which states in order for us to know if two functions are inverses of each other, both of these must be true. So actually you need to make sure you get all of this, but it's important to know that both of these must be true. And you saw problems like this back in the previous two lessons ago, or in lesson 8.2 I believe, where we saw problems like this where we put function g inside of function f. But if we ever do that, if we put function g inside of function f and we get x as an answer, that's kind of a unique situation. Because then if I put function f inside of g and I also get x as my answer, that tells me that the two functions are inverses of each other. So let's look at a couple examples. Let's look at this one here. We have f of x is 3x plus 11 and g of x is x minus 11 divided by 3. We want to figure out if these two functions are inverses of each other. So we're going to use the inverse function theorem to determine that. So the first thing I'm going to figure out is if this is true. Is f following g of x, is that going to give me x? That's what I want to figure out. So to determine that, I'm going to put function g inside of function f. So here's function g. So I'm going to put that inside of function f. So instead of 3 times x, it's going to be 3 times x minus 11 divided by 3 plus 11. So instead of 3x plus 11, it's 3 times function g plus 11. So now let's simplify this. So we know that if I have a 3 outside of here and we're dividing by 3 inside the parentheses, these two 3's are going to cancel out. So I'm going to have x minus 11 plus 11. And if you notice, when I go to simplify that, negative 11 plus 11 is 0, so I'm left with just x. That does not automatically mean that they're inverses of each other. I still have to do the other way around. I still have to verify by taking 3x plus 11 now, so put function f inside of function g. So I'm going to put function f inside of function g. So instead of x minus 11 all divided by 3, it's going to be 3x plus 11 minus 11 all divided by 3. Now notice how I didn't put this in parentheses. I could have, but there's nothing I'm multiplying the x by. So in this case it's not necessary because it would just stay 3x plus 11. But let's simplify the numerator here. When I do that, well, 11 minus 11 is 0, so I'm left with 3x over 3. And if you notice, the 3's cancel out, leaving me with just x. So the fact that I put function g inside of function f, and that gave me x as my answer, and I put function f inside of function g, and that gave me x as my answer, tells me that these are inverses of each other. Let's look at another example. Let's figure out if function f, which is 2x minus 8, and function g, which is 1/2 x plus 8, let's see if these two are inverses of each other. So my first step is to take f following g of x and see does that equal x. So I'm going to put function g inside of function f. So here's function g. I'm going to put that inside of function f. Remember, we're not adding these two functions together. We're not multiplying these two functions together. We're merging these two functions together. So I'm putting function g inside of the other function. So instead of 2 times x minus 8, it's going to be 2 times the other function minus 8. Well, 2 times, oops, forgot the x. So 2 times 1/2 would be 1. So it's going to be, so we have to distribute this. So half of 2 is 1, so it's going to be 1x. And 2 times 8, don't forget that, that's important. 2 times 8 is 16. Bring down the minus 8. But now 16 minus 8 gives me 8. Since this does not equal x, these are not inverses. So these are not inverses of each other. So I don't have to continue, I don't have to do the other one, because as long as this first one doesn't equal x, I can stop right there, because they both have to equal x in order for them to be inverses of each other. So that's the only thing new today as far as that's concerned. That's just taking what we've talked about with inverses, what we've talked about with the composition of functions, putting the two together to see that if I put function g inside of f, if I put g inside of function f and get x as my answer, and if I put f inside of function g and get x as my answer, then they're inverses. But there is one more thing that we're going to talk about, and that's how to limit or restrict the domain. That's going to be more what we hear. We're going to see that more often, how to restrict the domain to make the inverse a function. So all three of these graphs, if you notice, fail the horizontal line test. So even though each of these graphs that we have, the purple, the green, and the red one here, each of these individually are functions themselves, but since they fail the horizontal line test, their inverses are not functions. So we want to figure out how to restrict the domain. That means how can we put limits on the domain so that the inverse would be a function. So here's what I'm going to do. So again, the idea here is what we're going to do is we're going to restrict the domain. The domain is your set of x's. So what we're going to do is this. We're going to say for this first one, we're going to restrict the domain to say that x, the values for x's are going to be less than or equal to 0. Because if I say the values for x are going to be less than or equal to 0, that eliminates the other half of the graph. Now if you notice, this passes the horizontal line test. So by restricting the domain to be x is less than or equal to 0, we've created it so then that way it does pass the horizontal line test, so now the inverse would be a function. Now we could also say x could be greater than or equal to 0. Because now if I had restricted domain so our x's were just greater than or equal to 0, I would have a graph that would look like this. And if you notice, this also passes the horizontal line test. So this would also be a situation where we could restrict the domain, so the inverse would also be a function. So for a lot of these problems, there's going to be more than one answer. But remember, we're always looking to see what would restrict the domain to be. The domain is always your set of x's. So for this one, we could restrict the domain. One way to do that would be we could restrict the domain to say that x would be greater than or equal to 1. If I said greater than or equal to 1, what I'm doing is I'm saying from here over, so I'm eliminating the other half, is going to be the graph that I focus on. And that passes the horizontal line test. So by restricting the domain to be greater than or equal to 1, it passes the horizontal line test, so this part of the graph would be a function. Or I could say x is less than or equal to 1. Because if I say less than or equal to 1, I'm going to eliminate that half. And now this passes the horizontal line test, so this is a function, or so this inverse would be a function. Now, one thing that you would not say is if you said, if I said this, if I said x was, if I said that the domain was going to be x was greater than or equal to 0 for this one, that would be wrong because I'd be eliminating this part of my graph, but that would leave everything to the right of 0, which means that this would still fail the horizontal line test. So this would not be an option. Now technically, let me see if I can get rid of some of this. There we go. Technically, we could say the domain could be x is less than or equal to 0, because if I did that, I'd be eliminating this part of the graph. Doing so leaves me with this part, and this passes the horizontal line test, so you could say x is less than or equal to 0, but you're losing part of your graph that you could have still included. So that's why using these first two that we mentioned, greater than or equal to 1 or less than or equal to 1, would be the two best answers. Once you see if you can't restrict the domain for this next one, it's kind of tricky, but see if you can do it. Again, there's two possible answers that you could put here. So why don't you pause the video and hit play when you're ready to check to see if you have one of the correct answers. Okay, let's see how you did here. So for this one, again, we're looking at your values for x. Here we have where x is 3. If I eliminated that portion, so if I say that x is greater than or equal to 3, that eliminates all of this. And that portion of the graph does pass the horizontal line test, so that would work. That would be one possible solution. The other part that I could say, is I could say that x would be less than or equal to negative 3. Because negative 3 is down here, and if I eliminate everything else except for where x is less than or equal to negative 3, you can see that this passes the horizontal line test. So here we've restricted the domain, so this is also a function. But if I had said if I said the domain was less than or equal to 3, if I said the domain was x is less than or equal to 3, that makes it so it still fails the horizontal line test. So I can't say that because right here, if I draw a horizontal line, it's going to pass through this spot here at a whole bunch of points. So that is not an option. So these two that we have here would be the best two. Again, you only have to give one of these, but just know that for some of these answers, there are more than one possible correct answer. So that's how we restrict the domain to make the inverse a function. So with that, good luck on your assignment.